Okay, now your question.
0.5'e giden bir şeyden 0.5'e ileri falan hızlı olan oraya 0.8 falan görüyoruz ya. Hani
Now we see the speed as 0.8
yeah,
c.
0.8 and since as our speed increases, our acceleration decreases, like because of the gamma factors and like
Okay.
the transformation. How do we state that it decreases the inertia? Besides that, we know that the decreasing of the acceleration.
Well, what do you mean the inertia?
I mean resistivity to
Acceleration. So when I say that inertia increases with velocity, what I mean is that if you apply the same force to two objects of the same mass, the one that has a larger velocity, larger speed, will have a smaller acceleration. That is what is meant by the inertia increases with velocity. But who tells you that the force should be proportional to the acceleration, with the proportionality constant should be defined as mass? Newton said that. But we don't define the mass that way anymore. So that's not the mass.
So do we have to define inertia instead of mass in the modern physics?
Why do you need to define anything?
To define proportion, to define inertia.
Well, I will define the momentum as gamma times mv. Gamma is the usual gamma factor, m is the mass of the object, and v is the velocity. I don't define gamma times m to be anything.
No, what I mean was not defining gamma times m to be anything. What my question is, can we define an increasing inertia? I mean, how do we define that increasing inertia with decreasing acceleration as we increase the speed? Can we define such inertia, or does that inertia change?
Well, I already defined it, I think. I mean, or if you want, this defines it already. This tells me that if the speed of an object is larger, its acceleration will be smaller for the same force. This already defines it. This plus, of course, the force equation. These two equations already tell me that if the speed of an object is large, for the same force, I get a smaller acceleration. I don't need to define anything else. Other questions?
So, inertia is not a mathematical symbol in there, but it's embedded in two equations somehow.
Well, you see, inertia turns out to be not a property of the material, of the matter. You see, mass we define it as the property of the object itself. So you have a mass. Whatever you do, wherever you go, whichever state you are in, you have a mass. So that's why we don't like one of the reasons why we didn't like this definition of the relativistic mass. Because that thing, which we don't use anymore, basically depends on your current state. It's not just what you are, but it also depends on your current state. How fast are you moving? So it changes depending on your speed. It's not a property of you, so to speak. Yes? By defining like this.
Gamma final and gamma initial. Gamma final and gamma initial.
Okay. Gamma changes during the collision. V changes during the collision. And we say that if we define the momentum in this way, and if it is conserved in one frame, then it is conserved in every frame. Then how do you find the mass of an object? Well, the mass of the object is just E squared over C squared minus P squared. This is the mass of your object. So in the question in the exam, you know what initial energy is. Energy is conserved, so you know the energy of your system. You know the initial momentum of the system. Momentum is conserved, so you know the momentum of the system after the collision also. You know the energy of your system, you know the momentum of your system after the collision. That gives you the mass of your system.
I have a confusion about the inelastic collision and energy conservation.
Why?
Because in inelastic collision, energy should not be conserved
No.
in manners of
No. That's not how we define inelastic collision. What we call inelastic collision is a collision in which kinetic energy is not conserved. But here I'm not talking about the kinetic energy. I'm talking about all the energy of my system.
But energy dissipated.
Energy is not dissipated. Energy is still in my system. Some kinetic energy will be converted into the internal energy of my system, if we use the terminology of 109.
Our system consists of just two balls or their environment as well?
Two balls. There is nothing dissipated.
How do we know? How do we know?
Well, you are not given any dissipation. You are only told that you have two balls, nothing else, and they just collide and stick together. The kinetic energy, initial kinetic energy, will not be equal to the final kinetic energy. But the total initial energy will be equal to the total final energy. The energy that is not kinetic is basically the internal energy of your system. The internal energy, or let's call it mass, will change. If you heat a material, you are also increasing its mass. You are changing its energy, so it's at rest. You see, energy mass we define as the energy divided by c squared in the rest frame of your system. That is one definition of the mass. So if you heat your system, well, it's not accelerating, it's staying there. It just has more internal energy, but that means its mass increased. So,
and their inertia?
Not necessarily. Of course, it has something to do with it. You see, the mass is the energy, the total energy. Whatever contributes to that energy contributes to the mass. I repeat, it's the mass of a system is equal to its energy in its center of mass frame. So this is a kind of a generalization of the mass of mass of systems made up of more than one particle, let's say. You see, a photon should be massless. But two photons, you can define a mass to two photons. Well, just imagine going to the center of mass frame. The two photons are moving in opposite directions. This is the center of mass frame, so as a whole, my system is at rest, but it still has an energy. That is the mass of the two-photon system. You see, since mass and energy, they just convert to each other so easily, you cannot really say that mass is just the sum of the masses of the parts making your system anymore. That definition just doesn't make any sense. I'm not saying mass is conserved. I'm saying energy is conserved. That it was a true or false question, right?
The correct answer said that it was conserved.
Okay, send me an email, I will check. Other questions?
Hocam, ben inertia'yı şöyle anladım. Yani inertia bu momentum tanımının içinde kesinlikle var mı?
Well, you see, I would rather avoid concentrating on inertia. You see, we don't use that terminology. But of course, accelerating objects moving at fast speeds is more difficult, meaning you need more force to accelerate them. Now, I wrote that because you are so used to inertia.
Hocam peki ışık hızını aşmamızın nedeni, ışık hızını aşamamamızın nedeni bu işte hızlanan şeylerin daha fazla hızlanmaya karşı tepki göstermesi. Direnç göstermesi.
Well, that is the definition of inertia. Yes. Well, in fact, let's do an example. Let's pick a reference frame in which the object is initially at rest. So Newton's law tells me that F should be equal to d by dt of gamma mv. Well, let's say take the derivative. This was a gamma ma plus mv d gamma by dt. So what I'm trying to find is how does its velocity changes with time. We are exerting a constant force. This is gamma ma plus mv times, well, this is d gamma by dv squared, because gamma depends on time only through v squared, and then we have dv squared by dt. So the force is equal to gamma ma plus mv d gamma by dv squared, and this derivative is twice v dot a.
Why did you take the derivative with v squared instead of v?
As you wish, both are the correct, if you do it properly. Well, you see, v is the square root of v squared. If you want to take into account the vector nature, you have to use this one now. Now, d gamma by dv squared, this will be minus 1/2 because of the square root. Then we have minus 1 over c squared because of the coefficient of v squared under the square root. And we have 1 over 1 minus v squared over c squared to the power 3/2. So the force will be equal to gamma ma plus mv over 2c squared times gamma cubed times twice v dot a. Well, these two also, they can also cancel. So let me take out gamma cubed m. Well, here I have a 1 over gamma squared in the first term, which is 1 minus v squared over c squared, a plus v dot a. And again, remember, gamma is 1 over square root of 1 minus v squared over c squared. So as v approaches c, this term becomes infinitely large. If the force is constant, then this should get smaller and smaller. Acceleration should get smaller and smaller. Well, let's see. Now, in this problem, initially we are at rest. We are exerting a force, so it's accelerating in the direction of the force. So its velocity will be in the direction of the force. Its acceleration, the force is in the direction of the velocity. Force has two components, one in the direction of acceleration, one in the direction of the velocity. If you start from rest, you exert some force, it starts to accelerate. So its velocity will be, first acceleration will be in the direction of the force. So the change in the velocity will be in the direction of the force. So both a and v, they are both pointing in the same direction. So again, the acceleration will change the velocity, but still that change will still be in the direction of the force. Since we start from at rest, a, v, and f are all in the same direction. They are always pointing in the same direction. Now, why it will be important? Because it tells me that v times v dot a is in fact a times v squared. Sorry, here I forgot 1 over c squared. V and a, they are pointing in the same direction. So this has a magnitude v times a. This has a magnitude v. So this whole thing has a magnitude v squared times a, just like this one. This thing points in the direction of v, but the direction of v is the direction of a. So the left-hand side and the right-hand side, they both have the same magnitude and same direction. So they have to be equal. Well, if that is the case, if you look at the first line, the second term in A is the same as the last term, so they just cancel each other. So we have F is gamma cubed M times A. Let me remove the A. This is equal to gamma cubed M dV by dt. Well, let's see. Let me take the derivative of gamma with respect to v, as your friend had asked before. So this will be, I have a minus 1/2 because of the square root. Then I have a minus 2v over c squared because of the minus v squared over c squared. And then I have gamma cubed. So these cancel, these cancel. So this is equal to gamma cubed v over c squared. Or gamma cubed is equal to 1 over v d gamma by dv times c squared. So F is 1 over v d gamma by dv c squared times dv by dt. Let's continue. F is 1 over v d gamma by dt times c squared. d gamma by dt is fv over c squared, or f, okay, let me write it this way, f over c squared dx by dt, c squared. Or d gamma by dt is equal to d by dt fx over c squared. Or gamma is equal to fx over c squared. Now let's see. Let's say initially, let's say we start from x is equal to 0. So the force is in the positive x direction. So it keeps accelerating. It moves in the positive x direction all the time. When x approaches infinity, well, gamma approaches infinity, that is v approaches c. Only when my particle goes up to infinity, my speed actually approaches c at a constant force.
And there be a constant because of integral? And there be a constant because of integral?
Well, I just put some bound. I chose my initial condition so that that constant is 0. Well, let me add 1. Because I said that initially my particle is at rest, so gamma is 1. So these are all the constants. At t equal to 0, v is equal to 0, x is equal to 0. Well, why does the acceleration, why can't it, I mean, if it were moving at constant acceleration, eventually it will reach the speed of light c. But why can't it move at constant acceleration? Well, because of this gamma factor over here. Since f is constant, this becomes larger and larger as my object is accelerating, so a has to get smaller and smaller. Probably with some more effort, you can solve for v as a function of time t, but I don't think it will be more illuminating, let's say. Yes, any other questions? Try.
In the exam, we were required to calculate the change of the bar.
Okay.
When we calculated using the length contraction, most of us found a value between 0 and 1. However, when we calculated using Lorentz transformation, likewise, most of us found a value of around 2.
Okay, let's see. Okay, length contraction is probably, okay, so let's start with this one. We had, in the question, we had a reference frame, O. There was an object of moving with a velocity, let's say v, which was measured to have a length L. It's not at rest. Then there is another reference frame, O prime. Relative to O prime, this O reference frame was moving with a velocity u. So, A, what is the velocity of the object of length L? Well, it's just the v. Let's say v prime is v plus u divided by 1 plus vu over c squared, whatever you get. What is the length of the object? Using length contraction, first you had to find the length of the object in its own rest frame, which was L over, L is already the contracted length. So in its rest frame, it should have the length L over 1 minus v squared over c squared. This is its length in its rest frame. And now it is length contracted, and it's moving with a speed v prime. This is the length that it will be measured to have in the O prime reference frame.
Why otherwise? Why it doesn't work otherwise?
What do you mean otherwise?
Not finding the actual length relative to itself.
What do you mean? This is its length. Well, actual length doesn't have any meaning.
Relative to its reference frame.
It is this one. This is its length in its own rest frame. But we are not in its rest frame. Relative to us, it is moving with, relative to the O prime reference frame, it is moving with the speed v prime. So relative to its rest frame, its length is contracted. By how much? By this much. This is L0. Now let's go to C. How do we do it with Lorentz transformations? Now, let's identify some events. Let's say event 1, which happens at the point x is equal to 0 at the time t is equal to 0 in the O prime reference frame. This is the event. Let's say the left end is at x is equal to 0 at the time t is equal to 0. Let me define a second event. Let's say it is at the time t, and it is at the point L plus vt. The right end is at x is equal to L plus Vt at the time t is equal to capital T. So if we know this second event, we can determine the time of the second event. Just subtract the position of the right hand from the right position of the right hand, this v and t, we can determine the length of the object. Now let's go to, these are the events, the coordinates of the events in the O reference frame. Let's go to the O prime reference frame. So what I'm actually interested in that is delta E. If I look at delta E, which is E2 minus E1, once I determine this one, I can determine the length. Now, delta E would be, well, the change in the positions, well, gamma delta x minus or plus let me leave it for the time being, gamma delta t u delta x over c squared.
O prime was the outer or inner? O prime was the inner or outer?
You see, O prime is this one. You see, in the Lorentz transformation, delta x is the separation of the position of those two events in the other reference frame. This here we should have plus the speed of the other reference frame relative to us. Well, the speed of the other reference frame is plus u. Now let me put in some numbers. This is equal to, well, let me also say that this is gamma u. Gamma u, well, delta x was L plus Vt plus u, delta t was just t. Delta t is t plus u L plus Vt divided by c squared. Now this quantity over here is the length of the object if this is 0. You see, to determine the length, you have to determine the initial and the end points of your object at the same time. There shouldn't be simultaneously. They should be simultaneous, and simultaneity means that their time separation is 0. This is 0, and this is just the time. So this gives you what should be the t, and once you determine t, you put here that value of t, and you can determine L prime. And it is actually L prime should be something like 0.75 L. Okay, let's leave the midterm. Let us just finish chapter 2. Well, you see, we had discussed the Doppler effect. And when we were talking about the Doppler effect, what we had said was, what we observed is that on the average, the lights of all of the stars, again I repeat, on the average, the lights of all the stars and galaxies they have longer wavelength than their analogs on Earth, which basically told us that they are moving away from us. That was one thing we called the redshift. And looking at the redshift of the stars or galaxies, we can determine, one thing we can determine is their speed relative to us. And secondly, we can also determine how far away they are. Because observation tells us that typically, well, for a single star, it doesn't really work that well. But if you look at the star clusters or on the average, the speed of an object of the stars or galaxies that we can observe is proportional to their distance from us. And this proportionality constant is what we call the Hubble's constant. So if we know the speed of the object, we know the Hubble constants, we can determine their distance. Well, there is one more source of this redshift, so-called the gravitational redshift. So let's just imagine the sun or any star.
And by the way, that velocity is with respect to us.
Yes, yes, they are with respect to us. Now let's just imagine from the surface of the sun or any star, we have a photon leaving. It's just going away from the sun. Well, let's see, its energy here. Let's say this is the point A and this is the point B at infinity. The energy of the photon at the point A will be h nu plus the potential energy. Due to the gravitational pull of the sun or the star. And the energy at B, let's say this will be h nu prime. So the potential energy is negative. So nu prime will be smaller than nu. When this photon reaches us, it will have a smaller frequency, meaning a larger wavelength, and hence we have this, again, it will be shifted towards the red. If it's a visible photon, when it reaches us, it will be more red than when it left the surface of the star. Now, one problem is, what is this potential energy? How can we identify the potential energy of the photon? It's massless, but still affected by the gravitational pull. Well, we can use somewhat a Newtonian approach. Well, in Newtonian gravity, the gravitational potential energy was just minus the Newton's constant, the mass of one object, the mass of the other object, divided by their separation. This is what Newton tells us. But then, if this capital M is the mass of the star, the question is, what is the mass of the photon? We always said that the mass of the photon is 0. Well, we just make one assumption. Let's say U is equal to minus Gn m over r squared. Well, what general relativity tells us is that it is not actually the mass that is creating the gravitational influence, it's the energy. And so instead of the photon mass, we can use its energy. H times nu. This will be just some kind of an approximation, but let's see how well it works. E gamma, the energy of the photon. From the gravitational forces, the gravitational influences, let's say. And we already said that the photon is influenced by gravity. Yes, because the gravitational potential energy is negative. So let's put everything back. So we have h nu minus Gn m over Rc squared h nu should be equal to h nu prime, or h nu times 1 minus Gn m over Rc squared. This is equal to h nu prime. Well, this is, as I said, as you have seen, it's just a very crude approximation. We use the Newtonian gravitational law. We just made up some mass for the photon. But it's quite good. You see, the correction here would be a factor 2. You see, as the photon is moving away from the star, it should be losing energy. But we said that photon should be moving at the speed at c. Its speed cannot get smaller, but its frequency can get smaller. So that's basically how it loses energy, not because it is slowing down, but mainly because its frequency is dropping as it's moving away from the star. But then there is another problem over here. You see here, we are not putting any restriction on the mass or the radius of the star. But if r is very small, so that this number becomes larger than 1, well, that would tell us that nu prime should be negative. It just cannot be. That number is what is called the Schwarzschild radius. Basically, if you have a given mass, any photon, or in fact any object, that is closer to the center than this Schwarzschild radius, it just cannot leave. Because for it to leave, it means that it should have negative energy, eventually. But it just cannot be. So the photon cannot leave it. Center of the mass. So this is when we have the black hole.
Does it imply that photons do not exist inside that radius, or they can't get outside of that radius?
They just cannot get out. They are definitely trapped. We don't know anything about what happens inside. You see, on the other hand, we also discussed that if you are freely falling, you shouldn't feel the effect of gravity. So just imagine somebody falling into the black hole. He shouldn't be feeling anything. So if outside the black hole he sees photons, inside the black hole he should also see photons. But what happens inside the black hole, he still doesn't have an answer yet.
You meant by doesn't feel anything, but şey mi kastettiniz hocam? Hani düşerken ivmeyle yer çekimini ayırt edemiyor musun?
Yes. A small enough observer, let's say. If I added the correction, small enough observer. And if you have a huge black hole, the tidal forces will be small. This is the basic idea of the black hole. Basically, it's an object in which even the photon cannot escape. Yes, any questions?
Hocam foton kaçamıyorsa nasıl black hole radiation var? O sonra.
That is something different. They are not coming from inside the black hole, at least in one interpretation. They are coming from the surface. They are coming from R is equal to Rs. Okay, let's give a break now. Now we will start at 30.